So what about when we have a heterogeneous situation where we don't have aqueous this and aqueous that, but we've got solids and gases and liquids? For the equilibrium constant, we do not include concentrations of pure solids and pure liquids because their concentrations are constant. I mean, how do you find the concentration of a solid? Like solid ice. Its concentration is always the same, right? You can chop pieces off of it, but its concentration is always the same. And the same for a gas. I'm sorry, not a gas, for a liquid. The same for a liquid. Liquid water. It has the same concentration all the time. And so the equilibrium is not going to affect the concentration of the liquid. So we leave pure liquids and pure solids out of the equilibrium concentration, equilibrium constant, because they don't change. So for a reaction like this, where we have calcium carbonate forming calcium oxide and carbon dioxide gas, the concentration of a solid is always the same, and so we don't include the reactant or the product, this solid, in the equilibrium constant. We only have the concentration of the gas. And so the equilibrium constant is going to equal the concentration of the carbon dioxide gas that's formed. So how do we calculate an equilibrium constant? Okay, so first of all, let's talk about what is this M business. We haven't gotten to that. That's molarity. It means moles per liter. It's a unit of concentration. Okay, and we can do all of this without concentration. It's a unit of concentration. We don't really need to understand what molarity is. All we need to know is it's a unit of concentration. So that's what the capital M means. So if we have the hydrogen gas having a 0.11 molar concentration and the iodine gas having a 0.11 molar concentration and the hydrogen iodide gas having a 0.78 molar concentration, calculate the equilibrium constant. Well, the equation for the equilibrium constant for this reaction, it's the concentration of the product, here HI, and that's going to be squared because of this 2, and it's divided by the concentrations of these two multiplied by each other. So we're given here the concentrations of all the reactants and products, and so we stick the numbers in there and we do the math, and we come up with this constant as being 5.0 times 10 to the 1, or 50. And so that's kind of one of those in the middle. You might say, well, 50 isn't close to 1. It's a lot closer to 1 than 10 to the 15th is. You know, ballpark, it is pretty close to 1. So there's significant amounts of products and reactants in this one. Equilibrium constants do not have units. You say, well, but if I did the units, what would they come out to? We just leave the units. But we say that equilibrium constants are unitless. As long as you use the same units for the concentrations of all your reactants and products, then we just ignore the units. Any questions about that one? Here's another type of problem that can be done. If we are given the equilibrium constant and the concentrations of all of the reactants and products but one, we can figure out the concentration of the other. So here we're given the reactant and one of the products, and we're given the equilibrium constant, and they're asking us to find the concentration of the remaining product. So we write the equilibrium expression. It's the reactants raised to the powers of their coefficients divided by the concentration of the product raised to its power. And then we're trying to solve for this guy. You know what? Let's do this. What's the best way to do that? I would rather be drawing all this out for you, so I didn't get to editing all these slides yet, which is not good. Nice. Just do it again. I just pushed the wrong button. Okay, so how do we do this? Well, we first have to write the equilibrium expression. So KEQ equals the concentration of the products times raised to their powers, the power of their coefficients, which in this case is 1 for each of those, divided by the concentration of the reactant raised to the power of its coefficient. We're trying to find the CO2. Trying to find this one, CO2. So we need to rearrange this equation. So I'm going to multiply both sides by the denominator, and then I'm going to divide by the CF4. So we're going to end up with CO2 being equal to KEQ times COF2 squared divided by CF4. If you have issues rearranging equations like that, please ask me and I'll help you with that. Now we can plug the numbers into this equation. The equilibrium constant was 2.00. The concentration of COF2 was 0.255, and that's going to be squared. And the concentration of CF4 was 0.118. And we do the math. So we've got 2 times 0.255 squared and divided by 0.118, and I'm coming up with 1.10. And that is a concentration. It's going to have the same concentration units as the units that we started with. It's going to be molar, capital M. Any questions?